is that as I was preparing for this talk, I saw a news article, the New York Times, and this was written October the 12th, 1995. And some of you, of course, remember what happened. And then it talks about three-win Nobel Prize for work on threat to the ozone. And goes ahead says there are two Americans and a Dutch citizen who is based in Germany were awarded a Nobel Prize in chemistry yesterday for their pioneering work in explaining the chemical processes that deplete the ozone shield. And then, of course, it says this is, the scientists' achievement presaged the 1985 discovery of ozone hole over the Antarctic and led to a landmark environmental treaty banning the production of industrial chemicals that erode ozone. So what was actually interesting, and I liked this, was that although most scientists now accept the thesis that the ozone has influence, let me read it again. Although most scientists now accept the thesis, it still has influential critics outside the scientific community. The Republicans in Congress, for instance, have introduced registration to overturn the United States participation in the international ban on the production of the chlorofluorocarbon. So I think some of you may acknowledge that we are going through the same fight, people pushing back about the ozone, the climate stuff. So the same thing was going on. So when Paul started his journey back in 1984, when he came to Goddard, so this was what was going on. He came in 1984. In 1985, they announced the discovery of the ozone hole. And then from then, of course, everything is history. And he has been part of that story. So some of the things we're going to hear from him now captures this moment. So I wanted to reflect back on where Paul started in 1984 here at Goddard. He has been here 31 years, and he has done a lot of work. And in fact, he's doing a very important thing. He's one of the 4 co-chairs to the UN Science Panel for the Montreal Protocol. So he is actually in the thick of the whole story. So please, without further ado, help me to welcome our speaker, Paul Newman.
First, let me start off saying a few things. The first thing is that working here at Goddard since 1984 has been a real honor and privilege for me. It's amazing to work with such a vast number of really brilliant people and such a dynamic organization. But when Charles asked me to do this, just as a way of starting, just thank you everybody. This is going to be a little bit of a biography. It's going to be, because it's NASA, and we always do lessons learned at the end of missions. It'll be a discussion of lessons learned. So I'm going to start off by showing a little picture here, because somewhere in this picture is me. I bet you if you can spot me, hold up your hands. Can anybody spot me? Can you, Mian, you can? Okay, so this is me standing right here in the back. Okay, and the reason I'm standing in the back is because I actually have my leg in a cast back there. I broke my leg just before, in a game, just before this picture was taken, about a week before it was taken. And so I was sitting back there in a cast, and I'm on crutches there. But I wanted to say about this picture, it was, for me growing up, sports was the thing. Science was not the thing for me. I did not have a plan to arrive here at Goddard and do science when I was a kid. In fact, I had no plan to do science when I was a kid. I had a plan to be a professional athlete when I was a kid. Okay? And this was kind of the beginning of the end of that professional athlete story. This is O'Day High School in Seattle. So I want to show 2 big influences on me as I was growing up, though, that actually took me towards science. The first was the Seattle World's Fair in 1962. And they built the Space Needle. I was a little boy, and I could see the Space Needle being built. And here in this little area right here is the Seattle Pacific Science Center. And I would go down there as a kid, and they had just fascinating stuff there. I mean, stuff that it just blew my mind as a little boy seeing the stuff at the Pacific Science Center. It was really an emerging thing for me. Now, my dad was an engineer at Boeing, you know, and so there was kind of an interest in science. But the second thing was the moon landings when I was a kid. And that was really something to see the Mercury astronauts, to see the Apollo astronauts. That had a, and what was it to be on the moon? You could look up at the moon. It's an amazing thing. We're actually, we're there. So these two things had a real profound influence on me, besides being a Major League Baseball player. So now, let me just show you the difference, because many of you probably want to know what's the difference between me and the actor. And I just wanted to show you the difference here. So, first things first. Paul Newman, the actor. Okay, I want to make sure you all see this. And now, let's do the comparison of me. This is when I was on a field mission down in Mississippi a few years ago. Now, I have stopped smoking. That's the good thing. I got here to Goddard and I stopped smoking. Okay, so that's just a little bit about me. Now, I want to show you kind of the transition of the Newmans across the country. The Newmans have been, in fact, the Newmans go so far back in the US that I actually cannot trace them all the way back to where they started. I have no idea who the original Newman was who came to the United States, aside from the fact that I know he was somewhere here in Virginia in the 1700s. The first Newman that I actually find is living in a place called Campbell County, Tennessee. So I guess that, you know, really does make me one of the, you know, Appalachian byproducts here. They migrated down here to Indian lands in the 1830s, and then up into northern Missouri, which was the prairie at that time in 1842. Wound up here in Kansas, in the northeastern part of Kansas in 1858. They were all soldiers. In fact, a bunch of my uncles were soldiers in the Union regiments during the Civil War. In fact, a couple of them went down to this little place called Atlanta, and then they wound up marching down here to the coast with Sherman's army. So they were all farmers. None of them did anything of real note. They were just a bunch of farmers. In the 1920s, you can actually see them transition from rural folk to urban folk. My great-grandfather was living up here in Omaha, Nebraska, working for the railroad. And my grandfather was born up in Omaha here, and so was my dad. And and eventually, because of the Great Depression, they migrated out to Seattle. So that's how my family wound up in Seattle. This is the Newmans. There are other currents here. They're Germans that had come up from Phoenix. They're Finns that came over from South Dakota, actually from up here in Calgary through South Dakota, wound up down here in the Willamette Valley. So they're all Northwesterners. My extended family all sits in the Northwest. We have ranchers up in here in Idaho, farmers down here in Oregon. But mostly Seattle and Portland is where everybody in my family wound up. So that's my background, my family. So now you can kind of see, it was quick. And somebody said, you're going to put baby pictures in? I said, well, okay. So I put them in. This is my kindergarten report card here from Mrs. Scallon. And I actually knew Mrs. Scallon for many, many years because she was a friend of my mother. And so I just wanted to kind of show you. There's the back side of it. And I just wanted to show you a couple of examples here. My kindergarten report card participates in group discussions. Needs to make greater efforts. So all you shut up now. I don't want to, we're not going to have a group discussion. Expresses idea. Whoops, let me go back. Expresses ideas clearly. Well, I need work on this. Speaks distinctly. I don't know about that. I don't speak to. So this is my grade school report card. To put it mildly, I was a pretty ordinary, run-of-the-mill, average grade school student. I wasn't that great as a student. I was way more interested in getting out of school and going off and playing soccer or baseball or whatever with my buddies. So I was a pretty average kid. I just wanted to show you my first attempt at representing Earth science data. This is 1961. There you go. And I also, second grade, I actually took a stab at showing NASA-NOAA collaborations. So I wanted to actually, I figured I'd show you that. Here's NOAA down here, and here's the NASA. No, okay, let me just quickly skip through all my my career here. So here I'm in college. I went to Seattle University, and I want to show you the first is a guy named Reed Guy, who is a professor of physics at Seattle U. When I went to Seattle U, I actually didn't have any idea that I wanted, I liked physics in high school, but I didn't have any idea I was going to do physics. I got to Seattle U. I went there with a buddy of mine who is mathematics, and we were going to this freshman orientation, and they'd set up a bunch of these tables there at freshman orientation with different departments and so forth. You could talk to people in the various departments. And so my buddy was really into mathematics. He went to the mathematics table, and I didn't want to stand in line. There was a bunch of people in line at the mathematics table, and there was this physics table right next to it with nobody at it. And so that's how I wound up in physics. And this guy actually, probably more than anybody else, is what really influenced me in physics. A guy named Reed Guy, who's now professor emeritus at Seattle University. But this guy really taught me how to love physics, to actually look at equations and the beauty of equations expressing physical reality. He had just a profound influence on me growing up, and so I wanted to put him in here as an example. I think many of you have people like that in your lives, and he was one of mine. Now, I want to skip forward to Iowa State. These are graduate student pictures. The guy here on the left is Bill Randall. You can tell we're in graduate school. First of all, here's our graduate school accommodations. We were living in a forest. And then the one down here shows us, you can tell, here's Bill again, and here's me. You can tell we're the graduate students because we're the ones with bibs on. Mark Schoborough right here, and many of you don't know Dave Vinny. Dave Vinny and myself and Bill and Ann Douglas were all contemporaries at Iowa State. Mark had gone to Iowa State as an undergraduate, then would come back occasionally, and so this is how I made this connection to NASA. Now here's a nice group photo. You can see me with my fairly long hair. It actually got longer than that at certain points in my life. There on the left is Bill again. Here's Mark. This is John Stanford, Xinhai Gao, Russ Martin, who used to be here at Goddard, UNB, and myself. The one I really wanted to point out was John Stanford. Now, I told you that Reed Guy really made me enjoy and love physics. But John Stanford was actually the guy who really taught me physics. Going there, having to teach undergraduates in Physics 201 classes, having to prepare for the qualifiers. I really learned physics under John Stanford, and he was a tremendous influence on me. The other person to acknowledge here is Mark Schoborough. Mark actually was the one, he would come and visit Iowa State, and he's the one who said to me one day, he said, well, why don't you come to Goddard and do a postdoc at Goddard? And so he's the one who actually brought me here. So I arrived at Goddard in 1984. Charles already mentioned that. And here's some other people who had. I already mentioned Mark. Here's Mark. It was actually a picture of Mark in the DC-8. But Rich over here, Rich was the original, he was the head of the branch when I arrived. And then we transitioned to Bob Hudson and then Marv Geller. All four of these people actually, under Bob helped me write my first proposal. Mark guided me in the first couple of years here of being here as a postdoc. Rich was actually the one who actually kind of pointed me in the direction of thinking and understanding stratospheric ozone. So let me just say that here's my rule number one. There is no such thing as a self-made man. And I think every one of you can probably look at your lives and you know who are the ones who actually pointed you to this place where you are here and now. You know who they are. And in fact, I just wanted to acknowledge them. I didn't really talk about my mom and dad, but huge influence, teachers, mentors, coaches. Some of the coaches were actually good and some were bad. Actually, there's a few people in my life who've been negative examples. That is, whatever you think they would do, you do the opposite. That's probably the right thing to do. I already mentioned Reed, John, and Mark, and Marv. So that's the first rule. Now, I did mention that Reed Guy taught me to love physics. I just wanted to show you Here, this is another thing from 1960. When you go and you do these Maniac Talks, you dig up all sorts of fun stuff. So here's 1964, and this is a little Valentine I sent to my mom. And here you can see Happy Valentine's Day from Paul. And actually, it's great. Look how I spell Valentine. Valentine's. And I have the example right here of it properly written. I don't know. Okay, so now Charles already mentioned that in 1984 I got here, I was doing work on actually parameterizations within 2D models. And this paper came out in 1985 showing this really precipitous decline of ozone at Halley Station down over Antarctica. And here are the three guys who wrote that paper, Joe Farman, Brian Gardner, and John Shanklin, standing in front of a Dobson unit that actually made these measurements. And so this was a really profound, I mean, 1985 was a year of decision in atmospheric sciences. And it really starts with this paper. It was also the year the Vienna Convention was signed, which actually outlined ozone as being a problem. So you can add the satellite data on top of this. Here's the BUV data, and the red points here show the Nimbus 7, and they're in pretty good agreement. These are actually the Halley data, but these are the red points are actually the lowest point in the October average. Now this was followed by this image. And this is why we call the ozone hole the ozone hole. So this was made by P.K. Bartia down here in the corner here. And here's the picture of the ozone hole, kind of a funny color scale, but it shows this very, very large depleted region over Antarctica. And I think there's nobody who can really tell us how the word ozone hole got coined. It started really early on. I mean, certainly by the summer of 1985, people were calling it the ozone hole. A lot of people think that maybe Sherry Rowland coined the term. But by 1985, people were calling it the ozone hole. And this is the image that really started that. And this image actually, every few years, we write a big major assessment of what's going on with atmospheric ozone in the stratosphere. This particular image wound up in atmospheric ozone 1985. And that's the document that really formed the basis, the scientific basis for the Montreal Protocol. Without this big, giant, 3-volume set of information on ozone, scientific information on ozone, the Montreal Protocol would not have been signed. And this thing, this ozone hole, sat as a backdrop to that agreement. Now, just to give you a little information here, here's a picture of the ozone hole, and here's the size of the United States. You can see Antarctica on the background. You get a size scale here. It's a big ozone depletion. Now, rule number 2. If you don't know where you're going, any road will get you there, okay? So I didn't know where I was going when I got here, okay? It's luck. It was just lucky that I arrived at the time when the ozone hole popped up. And people really didn't know what was going on at the time. It was, like I said, it was a real shock to the community. And there were 3 theories that were developed. There was, it's called the solar theory, but it's NO and NO2. These 2 gases catalytically destroy ozone, so there's a lot of NO and NO2 over Antarctica, and that leads to a lot of depletion. There's the dynamical theory. So you have very little ozone down in the lower stratosphere and down in the troposphere, and if you could lift this, you could create a reduction of ozone over Antarctica. Not really a depletion, but a reduction, just by lifting low values into the lower stratosphere. And then there was the third theory. Chlorine from chlorofluorocarbons were being released from reservoir species. They come from CFCs, and they react on the surfaces of polar stratospheric clouds to release reactive chlorine, which would then attack ozone. So this is the third theory. So now, this is sort of the state of affairs in 1986. There was a few papers that I had written, one in here in which I suggest correlations of temperature and total ozone from year to year, suggest a single mechanism behind both trends. Here's you can see this is the temperature trend, and here's the ozone trend as a dotted line. So these 2 things are correlated. We didn't have a lot of years here, but that was very suggestive that the mechanism was exactly the same, although the trends are a little bit different, as you can see. Back here, you can started doing a little photo bomb here is Joan Rosenfield. And there's Mark Schoberl hiding his face. This is when we're all over in Building 21. And so everybody was excited about what was going on with the ozone hole. So now in 1987, they developed a mission to go down and take a look at what was causing the ozone hole, to sort it out between these three particular theories of the ozone hole. So this was the Airborne Antarctic Ozone Experiment. And there was a number of measurements on here. I've only highlighted a few of them. There was measurements of nitrous oxide, N2O. Now, N2O is emitted at the surface. It's destroyed in the stratosphere. And so you get a gradient. A lot of it down near the surface, very little of it up in the high stratosphere. And so if it was this lifting theory, you'd find low ozone in association with very high N2O. So laughing gas is a great gas. We all love it. Particularly when we go to the dentist, I guess. Then there was this NOx idea, NO and NO2. So high NOx levels should be associated with low ozone. And then the third one is the chlorine test. We ought to see high chlorine and bromine levels would be associated with low ozone. So here's the ER2. Here's actually a picture from Punta Arenas. Here's the hangar that we were in. I think Susan Strom, this was your first mission you were on. Brand new postdoc. So, and Susan was working on this particular nitrous oxide instrument. Now, here's the, this is an instrument from Harvard. This measured CLO. There's another instrument, you can't see it, that measured ozone in situ. So now, here's a couple of flights. This is flying down from Punta Arenas down into the polar vortex. And I show two plots here, one from August 23rd, 87, and one from September 16th, 87. And what it shows is, we would have expected chlorine levels, CLO, to be down here, somewhere in here. Instead, it was much, much higher than that. Here's ozone over here. And this is early on as the sun is just starting to rise over Antarctica. Now this is almost a month later. And now you can see, going down into the vortex, you get into the vortex down in here, you can see these anti-correlations where you have higher CLO, you have low ozone. So ozone was declining. It was going up here at these middle latitudes, but it was declining over Antarctica, and it was directly in association with a high chlorine. And now there's no way that you could get this high of chlorine without this, without this release on polar stratospheric clouds of chlorine species. So, and in fact, I didn't show the N2O measurements, I didn't show the NOx measurements, but they absolutely destroyed this dynamical theory which I had been writing papers about, okay? So, that gets you to the third message. You need to learn how to handle the truth, okay? And this was a hard lesson, actually. I mean, in principle, we say, you know, we're scientists, and we get this information, and, you know, the facts are what the facts are. But you'll find that that's hard to do. It's hard to accept that, in fact, I'm wrong, they were right, time to go back and reformulate what I've been doing for the last 10 years, 40 years in my case. In any case, so these measurements, and they call this, actually this plot, they called it the smoking gun plot, because it proved beyond a shadow of a doubt that it was chlorine from CFCs that were causing the Antarctic ozone hole. So the next question is, okay, given that it's happening down over Antarctica, is it happening over the Arctic? So that brings us to the next thing. And this is the Arctic Airborne Stratospheric Experiment. So I'm going to show a few pictures from here. It was using the ER2 and the DC-8, just like was used down over Antarctica. It was flying from Stavanger, Norway in 1988-89. Now here you can see, this is Leslie Alate right here, and you can see him right next to his computer, as you'd expect. It was a pretty big computer, actually, at that time. And so we had actually hauled that computer to Stavanger, Norway, and we were there in the squadron hut looking at meteorological analyses and the data from day to day. Here you can see Rich Stolarski describing a plot of a model simulation. And here is Mark Schoberl. He's actually showing some PV chart, potential vorticity. This is a jet, and he's explaining actually why you would expect to see various trace gas distributions. And so we'd have these almost daily science team meetings. And in fact, So moving on from there, so we were there to look and see if we would find high chlorine. The answer was that indeed we did. But let me say something about ozone levels first. You can see this is in 1988 when we actually went. And here's the northern hemisphere in March. Here's the southern hemisphere in October. You can see a big jump up. And so we were kind of looking at, not maybe a little drift, but it's hard to say there was anything going on in the Arctic. But with time, you can see that, in fact, that things have gone down over the Antarctic and stayed down. Maybe a little bit of a hint of a little rise here. And things went down in the Arctic. You can see there have been years that have been really, really deep. This is because those are really cold years. Now, this is a plot that Eric Nash, over time, has helped me put together. Eric has been one of the people who has done, provides a lot of the background work here at Goddard. A lot of the stuff here and in Code 614 wouldn't get done without Eric. Now, one of the things that Charles mentioned at the start was there are skeptics, okay? There was a lot of attack on these ideas of ozone depletion. Here's one. This was a book written by a guy named Rogelio Maduro. And in fact, this became quite the popular book amongst the skeptics crowd, even though almost every page of the book is filled with half-truths and misuse of facts. And you would show up, you would give a talk somewhere at AGU or wherever, and people would appear and they would have the book in their hands or in their back pocket, and they would ask you questions straight out of the book, okay? And so that brings you to the next thing. Never argue with an idiot. People watching may not be able to tell the difference. So I'm going to give you an example of how to get around this, because of course, if somebody states a falsehood, you just can't let it go a lot of times. And the operative word here is argue, okay? Let me go. So now, I learned this lesson pretty well from this guy here. This is Sherry Rowland, and he's the one that Charles mentioned had won the Nobel Prize in 1995. This is me in the background. I'm resting my eyes. But Sherry, I was at a meeting at AGU shortly after this Hole in the Ozone, or this Rogelio Maduro book came out. And Sherry we had given a series of talks. We had a little panel up there, and we'd given a series of talks about ozone depletion. And Sherry was sitting there. I don't know if Rich is here, but Rich will remember this incident too. And somebody has the book in their hand, and they said, well, everybody knows that the ozone hole is caused by volcanoes. And Sherry says, I see you have the book. He says, please bring it to me. So the guy brings it up, and Sherry had not only read it very carefully, had memorized pages. So he would open it up to pages. So here's what we read that Mr. Maduro says, and here's the actual facts behind it. Okay? So then he gives the guy the book back. But this guy isn't done. He's angry. He's a red-faced guy. He's sitting there. He's really mad. And he's raising his hand. He's shaking his hand like this. And Sherry goes very calmly. He says, thank you. I think you've had your questions. Let's let the other people have questions too. And so Sherry didn't argue with the guy. He took what the guy was trying to, he took the guy's question, he answered it with facts, and he moved on. He did not argue, okay? Now the other part of that, never argue with an idiot. Make sure you're not the idiot when you're doing the argument. I'm just saying. Many times I've been in bars. No, wait a minute, I've never been in a bar. So just to go back to that point about volcanoes, and this one comes up a lot, did Mount Erebus cause the ozone hole? So I actually I have a big set of these skeptics questions I have in presentations, and I just keep them handy. And when they come up, I will go, oh, that's a good question. That's a very interesting scientific question, and I'll go to it. And then I do exactly what Sherry did. I said, well, you asked a question. Let's let the other folks have questions also. So you can move through these things. And it's a great thing because you're probably not going to convince the angry guy in the audience. He's there to get you. He wants to show you up. What you're talking to is everybody else in the audience. The other, 40, 50, 100 people, whoever is in the audience. You're talking to them, and you're talking to them about science. You're not arguing them about something in a book, okay? So, now back to some of these things about ozone. And I'm going to talk a little bit about an experiment, the SAGE 3 ozone loss and validation experiment, SOLVE, which was done in the year 2000. Again, it used the DC-8. Here it is, and here's the ER2. Here's a picture of the pilot getting in. This picture, I can't remember exactly the temperature, but it was something like about minus 19 Fahrenheit when they did it. The amazing thing is this guy named Jim Sokolic. You can see he has no gloves on, and he's just got a light sweater on. It was minus 19 Fahrenheit. Now, the explanation from that is he's from Wisconsin. Okay. Here you can see Mike Carrillo. Mike Carrillo was the program manager at the time, and Mike actually had you can see SAGE 3, the Stratospheric Aerosol and Gas Experiment, which measures ozone and aerosols and so forth. So they were launching this on a Russian Meteor 3 satellite, and Mike had the wisdom to recognize that we ought to do a validation experiment in association with this. We could go back to the Arctic to do that. So I just wanted to use an example of here, somebody from headquarters who actually, used a little thinking. It's shocking for headquarters, isn't it? But Mike had a really well thought out idea to go up and do a big mission like this. And we went and we actually, once again, this is a picture showing latitude and various, this is chlorine here. This is total chlorine in black. This is HCl and chlorine nitrate. And this is in terrific agreement with what theory would tell you was happening inside the vortex and outside the vortex. So really great. And there's a number of here's the measurements from the Harvard instrument CLO, the chlorine dimer, HCl and chlorine nitrate from JPL in Harvard. It was a really nice experiment. It was one of the first experiments. This shows Mike, D. Lewis Porter, and myself. It was one of the first flights of the U-2 back over the ex-Soviet Union. This was in the year 2000. And so we actually had the ex-Russian, the head of the Russian Air Force, the Soviet Air Force actually, fly with us on the DC-8. And we actually flew the U-2 down over Russia. A nice example of cooperation. I'm not sure it could be done in today's environment. But, cooperating on an international level to achieve some scientific goals. Now, we did have Goddard management with us there. And they were very helpful. So now I want to move on to go on a little bit about ozone depletion. And it brings me to rule number 5, okay? And this is for all of you. We're at an institution where we have some incredibly smart people here, okay? That brings you to the second part of the sentence here. Get out of your office and talk to them, okay? The only way you're really going to, if you sit in your office and you do your little thing, not only are you going to miss out on really interesting stuff that's going on around you, but you won't be part of it either, okay? You won't be able to make a contribution to really interesting stuff. So get out of your office and talk to people around the building. It's really good to do that. And I do that because I've got 2 people here. One is Luke Oman, and Luke is sitting right here. And Ann Douglas right here, who's she's got the whole world in her hands. I'm not going to sing, don't worry. There are a few other people on here, but we did a simulation, and I wanted to see if I can show that simulation. Here we go. And this is a world avoided simulation in which, chlorine's going to go down because of the Montreal Protocol. See the date up here. Here's chlorine concentrations, and this is total ozone that you're looking at. So red, that's high ozone. Blue is low ozone. You can see the chlorine amount for different years. They're roughly tracking with one another. But the Montreal Protocol, it slowed down the growth of chlorine. In the world avoided, we just assume it keeps going up 3% every year. And you can see the formation of the ozone hole down here. You can see it in both of these worlds. And with time, you'll see this is going to kind of slow down because of the Montreal Protocol. This is going to keep going up. And as you can see, they look at the difference between these two. You're getting deeper and deeper ozone holes here compared to there. Now you can see that it's almost more than a factor, almost a factor of 3 higher in ozone, or in chlorine than over here. If you look up here in the Arctic, you'll start seeing ozone holes form over the Arctic, deep ozone holes getting down to these bluish levels. And if you look overall, you can see the reds now that typically appear in the high Arctic every year, they've disappeared. The reddish colors and yellows you see are disappeared from around Antarctica. And as it goes higher and higher and higher, you're going to see ozone go lower and lower and lower in the tropics. So now you can really see the distinction. Here's really high ozone. Here's really low ozone. Natural ozone is about 1.2 parts per billion. And so you can see now it's on the way down. It peaked out at about 4. By the year 2050, it's 2.7. Here it's up to 37. And now you can really see that ozone is really going away. By the end of the simulation in 2065, 2/3 of the ozone layer is gone in this particular simulation. Okay? Now, the reason we were able to do this really dramatic demonstration of what would have happened without this international agreement is because there are people like Luke, there are people like Anne. Anne was, I think, the one who originally programmed up a lot of the chemistry in this model. So that makes my point. Get out of your office, talk to people. Okay, so now let me touch a little bit. All this ozone work over the years, I got a call back in 2006 from a guy, Dan Albritton, who historically had been running the scientific assessment for the Montreal Protocol, attended all the Montreal Protocol meetings. And Dan asked me if I would be interested in taking over this job of going to these diplomatic meetings, helping to organize these scientific assessments. And I must admit that my first inclination was no. It struck me as something that really required, like a headquarters person, somebody with a little more diplomatic experience, somebody who knew how to handle, the mucky mucks. And at first I thought no. I talked to a few people, and I kind of convinced myself that, it would be interesting. I never convinced myself I could actually do the job. I convinced myself that it would be interesting to try the job. And so I don't have another rule here, but there is a rule about, don't be too afraid to actually, move off the norm, okay? Try to do things new. Let me say a few things about what the Montreal Protocol is. I already mentioned the year 1985. 1985 was when the Vienna Convention was signed by the world's nations. Every nation of the world has actually signed the Vienna Convention. And the Vienna Convention actually doesn't regulate any chlorofluorocarbons, any gases. It simply recognizes that there's a problem. That's all it really does. The Montreal Protocol, which is kind of a sub-agreement to the Vienna Convention, is the agreement that regulates the production and consumption of ozone-depleting substances, okay? So it regulates production and consumption. It doesn't regulate it at the level of the consumer. So, there's nobody coming and testing to see if your car air conditioner has a CFC in it or you're using it in your home air conditioner. What they're doing is they're actually telling individual countries, you can produce and consume this amount of CFC. Every country has a specific level that they can produce and consume. And now that level for the world, every country in the world is 0. There is no country that can produce or consume chlorofluorocarbons now. There are still some banks of chlorofluorocarbons out there, but there's no longer any production or consumption. They also did a couple of clever things. The Multilateral Fund, it's actually a fund that is used to give countries money to report, make sure they can collect information, report on their production and consumption. It also re-examines control measures. They actually pay out a little money for projects to go out and get CFC. So they could, project comes up, a couple guys are going to get some trucks and drive around the country and go to landfills and find old refrigerators, vent the CFCs out of them. The Multilateral Fund can actually pay for that. And they've done little projects like that. And the third thing is they have 3 assessment panels. So all the diplomats sit in a meeting and they have 3 panels, the Science Assessment Panel, the Technology and Economic Assessment Panel, and the Environmental Effects Assessment Panel. And so this is the panel that I fall under. So that brings to the next thing. What is the assessment panel? Under Article 6 of the agreement, every 4 years, we actually write a very large document telling them what ozone is doing and what all these CFCs and other gases are doing. In fact, replacements for CFCs also. So in fact, we just completed that. And in December, we published that very large document online. So they've been doing this, as I already mentioned. It's been going on for a while now, and we do it every 4 years. So 2014 was the last one, but we did one in 2006, and we did one in 2010, 2002, and so forth. So the co-chairs are, were chosen and approved by the parties. So they actually, for me, I wasn't actually there when they voted on it, but they put your name up. They kind of describe who you are, and then the nations vote on it, and it's done by consensus. So in these diplomatic meetings, and I'll show you a picture of one of the diplomatic meetings here. You can't quite see it, but every table, they've got a little card in front of it. You can just barely see some of these cards. And that indicates what country, so they don't have little flags, but everybody's got also headsets here, so you can listen to different translators. So every country most countries are represented. This was in Doha, Qatar, back in, I think this was in 2010, was this particular meeting here. So they sit around, and of course, what you do is you'll give presentations about ozone depletion and so forth, and then your job is done. Then it's an interaction between the parties about whether they're going to increase regulations or not. Oops. Let me see if I can get this to run. The Montreal Protocol is an evolving agreement. So this sort of shows what they do is they attach amendments to it. So when the Montreal Protocol was first signed in 1987, the regulations simply slowed the production and consumption. It didn't actually stop the production and consumption of ozone-depleting substances. But all these other agreements actually did. Now, this is where the scientists actually sit. We sit way in the back here. It's myself right there, and there's Mike Carrillo. Mike was the chairman of the Ozone Research Managers. The Ozone Research Managers, the international group of Ozone Research Managers, meet every 3 years, and they write out an agreement on what are the science priorities for the next few years. And then they deliver that report to the parties. So just another word about the parties. It's actually quite interesting sitting with these folks. They're not scientists. A lot of times when you're reporting on scientific information, there's really only 2 or 3 people in the entire audience who really understand what you're talking about. So if you talk about a compound like CFC11, and if you had a show of hands, how many of you can write out the chemical formula for CFC11? Now they're all delegates to the Montreal Protocol. There's probably 3 or 4 people who could write out the chemical formula. The people who can write out the chemical formulas are sitting back here. But these people are real experts on technology and the diplomacy behind all of these gases. Okay? So the fact that the United States was using, it still uses a particular ODS called methyl bromide, which is used to fumigate wooden pallets that come into the United States. Pallets with bananas in them. They still fumigate with methyl bromide. And the fact that they do that is because there's an exemption for methyl bromide that is made by all of these folks right here. Okay? And the US delegates recognize it's important to keep invasive species out of the United States. And so we need that. And so they will argue for that. So all these countries have their own particular, they understand what methyl bromide does to the stratosphere. But because of the other requirements, they have made an exemption for this. This is what these folks do. And they're very, very good at it. They're not scientists by any means, but they're very good at the diplomatic parts of these agreements. So that brings me to the close. I'm just going to thank everybody. I've got a little photo bomb here I can show. Here's Anthony Didlig right there behind me. This was during the HS3 mission. I didn't really go into HS3 and some of the other stuff that I've done. There's a number of other things, but I figure this is some of the stuff I've covered today is maybe a little more interesting. So I apologize, I've mentioned quite a few names. And as I mentioned, I was using the talk, Maniac Talk, as kind of a thank you to a lot of people who have helped me over the years, who have worked with me over the years, and comes back to that point of you know, get out of your room and talk to people. So thank you.
Okay, time for comments, questions. Do you have any?
You told us a delightful story, a small group of us, about your briefing one of the U-2 pilots and turning around from your PowerPoint presentation, and one of the fellows was right in your face. Would you care to comment?
Well, you know, yeah, it's actually, I think, an interesting story. Let me see if I can go back and find the slide. Not this guy I'm going to talk about, but you look at this plane, it's a single-engine plane. And they were flying this. In this particular case, we're flying from above the Arctic Circle. We're flying out over the Arctic Ocean up to the pole with this plane. If anything happens to that engine, he can glide about 200 miles or so. It's got a large wingspan. But he's going to wind up either in the Arctic Ocean or on the ice. Now, this looks like a thick, bulky suit. It's a full pressure suit. But it doesn't really insulate you at all from the cold. And so he probably, if you went down in this plane over the Arctic Ocean, there is no air-sea rescue for 1,000 miles. You're pretty much dead if you land in this plane. And so, and this was actually not during this mission, but it was during this mission, AASE-2. And we had a guy whose name was Ron Williams, and he was a pretty tough cookie. He was one of the old U-2 pilots, old school U-2 pilots, who had done a lot of flying for the Air Force and the CIA. And Ron, we had asked Ron to do a rather tough assignment, and so we had briefed him on this. And Ron got pretty mad about it because we were pressing the envelope of what we should be doing, both from a safety viewpoint and from a scientific viewpoint. And Ron, his statement to me was, "I risked my life for my country. I am not going to risk it for science." Fair point, okay? I cannot argue with it. So basically, we had to actually lay out why a lot of times we'll talk about, we're going to fly into the polar vortex and we want to get to these sort of solar zenith angles and we want to see high CLO and whatever. These guys are not scientists. You have to explain why that's important to them, to make sure they understand the broader context of the mission itself so that they are willing to make these risks. And so that's what we had to do. We had to sit down and explain to him in detail of why we had to do that. It happened to be a second time, actually. So that was the first time it happened. It happened to be a second time just before we flew on this mission. And we had a group of these ER2 pilots, and I was out at what was then Dryden. And they basically collected me into a room. And once again, they asked, it wasn't Ron. Ron wasn't there that time. He had retired by that point. They got me into a room and they said, why should we risk our necks for this particular science? And I had to convince them. And that's why they flew this mission. It's because they recognize the importance of the science.
I find that if the pilots of the ER2 know what they're after and why you're trying to do it, they can sometimes improve the mission themselves. Because they're pretty smart too, and they can see what's going on. I mean, we look at clouds and aerosols, so it's a little easier to see than CLO with your eyes. But these guys often improve the mission because they know why we're trying to do and what we're trying to do.
Yeah, it's important to brief the objectives properly.
And it's good training for science and the American public in the broad scheme of things.
That's exactly right.
I have a question for you. How do you explain the polar vortex?
So the polar vortex, okay, you all hear this term all the time. It's a total abuse of what we mean by the polar vortex. It pisses me off. I'm sorry to say that. It makes me angry. So the polar vortex is a large jet that goes around. It's the region interior of this jet that circles the polar region, okay? And it's massive in scale, okay? Extends, its average position is down around 60 degrees north. So it's a very, very large phenomenon. Now it extends, it sticks up in the stratosphere, extends well into the mesosphere, and it comes down into the troposphere. It penetrates a little bit into the troposphere. But these cold Arctic outbreaks that we see down here in the DC area, they are not the polar vortex. Completely different thing. And the polar vortex is actually, in fact, Mark Schoberl wrote a paper called On the Structure of the Polar Vortex. It was written, and he shows how it extends down and everything. There's a lot of detail. And suddenly somebody decided to use a catchy term. I don't know who did it, but I'm going to get that guy. And it does sound catchy. The polar vortex is coming to get you. But it's really, it goes back. There's the old meteorologists talked about air mass theory. And so talking about the polar vortex goes way back to old air mass theory. But it's still, even back in the day, wasn't right. So, yeah.
So having learned all this about from the ozone experience, what would you advise for those who are trying to solve the problems dealing with global warming?
You can either choose to ignore it, that is, okay, I'm just not even going to begin to argue it, or you can just state the case, okay? Here's the temperature trend. This is what it looks like. It's going up and up and up. If we can take models, which, it's our collective physics, chemistry, dynamics, radiation, about how temperatures are changing. If we run these models, without climate gases, we cannot get this trend. We have to run them with climate gases to get this trend. Don't try to get into an argument with these people. State the facts, move on, okay? And then, a lot of these people, they're not going to accept your, what you say anyway. With time, maybe, but you just kind of have to live with that now. Now, the other side of the climate, and I will say something about the Montreal Protocol, just to add on to this, is that one thing I didn't mention is that the CFCs that we used to use have been replaced by alternative compounds. So every car air conditioner out in this parking lot has a gas called HFC 134A in it. Well, that's the propellant you use, or excuse me, that's the carrier gas you use in your car for air conditioning. Now, HFC 134A has a global warming potential of 1,400. What that means is it's 1,400 times more efficient than CO2 as a radiative gas. Okay? So 1 pound of CO2, or excuse me, 1 pound of HFC 134A is equivalent to 1,400 pounds of CO2. Okay? It's a really efficient trace gas for climate. The HFCs exist because of the Montreal Protocol. So we went from the CFCs and we replaced them with HFCs. Now there are but HFCs also have long lifetimes. So they're contributing, the Montreal Protocol has effectively contributed to the climate problem, okay? Solve the ozone problem, but it's contributing to the climate problem. So HFCs could be regulated under the Montreal Protocol because they are environmentally, climate changing gases. That is actually under negotiations right now. There is a meeting in Bangkok in May to discuss this. And then the next Montreal Protocol meeting is next November. The United States, Mexico, and Canada have what's called the North American Agreement, and they're trying to push these HFCs. It's part of the administration, the Obama administration's policy is that HFCs should be folded underneath the Montreal Protocol, and that may in fact happen. So just as a side aspect to this whole discussion of climate, many of these gases that have been created because of the Montreal Protocol, they aren't ozone depleting gases, but they may wind up under the Montreal Protocol because of climate. Joe?
Dynamic connection between the ozone hole and what's happening at the surface in Antarctica?
Oh, that's a good question. There's a lot of interaction. Turns out that the ozone hole, it leads to a change of the southern hemisphere stratosphere. So winter, because you deplete all this ozone, when the sun rises, you're not absorbing UV. And so you've lost a source of heat. You also, because there's no, ozone is also radiatively active in the IR, you don't get any absorption of upwelling IR radiation. So what happens is the polar lower stratosphere stays colder for a longer period. In fact, if you look at you can look at the disappearance of the polar vortex, and you can see that the polar vortex over Antarctica disappears at a later date now because of the ozone hole. And it's in really pretty good agreement with theoretically what we expect. So we see these temperature changes over Antarctica. We see the changes in the vortex over Antarctica. Now what that does is that leads to a little bit of an acceleration of the tropospheric flow. And so the flow around Antarctica, about 60 degrees north, stays stronger all the way down to the surface because of the ozone hole. Now what that does, that changes the wind stress on the ocean, which then changes the ocean overturning circulation in the southern hemisphere. Because this jet is a little bit stronger, it changes rainfall patterns. It changes the structure of tropospheric cyclonic systems. And so all of these things have now been written about, okay? You see all of these changes in the southern hemisphere because, southern hemisphere troposphere, because of the Antarctic ozone hole. So the ozone hole not only has an impact on UV at the surface, it also has an impact on climate in the southern hemisphere, a very profound impact. You can't explain things in the southern hemisphere without understanding the ozone hole. Okay, I think we've hit 1 o'clock.
One more time.